Yes, so my name is Dmitry Kuznetsov, and I'm presenting my joint work with Adam Morrison today. I'll be talking about Privbox, as we have mentioned, is a mechanism for faster system calls through sandbox privileged execution. Now, I'd like to start by talking a bit about system calls. System calls are the main way processes request services from the operating system. System calls are very similar in usage to a function call, as in both cases we prepare parameters, perform the invocation, and receive the result. However, unlike a function call, system call invocation is orders of magnitude slower. And this has to do with the system call invocation involving many more steps, both in hardware and software. For example, the change of hardware privilege level. Further, if we take into account spectral and meltdown mitigations like PTI or page table isolation, then system call overhead becomes even worse. We can see in the graph below that while a simple function call has overhead of about 20 cycles, a system call takes over 500 cycles. And if we look at system call with PTI mitigation, overhead goes to over 900 cycles. Naturally, system call overhead is bad for system call intensive processes. And many workloads are in fact system call intensive. If we recall, most I/O operations eventually translate to system calls. So I/O intensive workloads suffer greatly from system call overhead. Now let's look at a theoretical Redis-like workload and assume that it runs at about 200,000 requests a second, and that each request requires at least two system calls, one to read the request and one to write back the response. Now, if we recall the number from the previous slide, where system call overhead is roughly 900 cycles, and if we add everything up and assume a modest CPU of about 2.6 gigahertz, then our theoretical workload spends at least 13% of its cycles on system call entry and exit. Now, reducing system call overheads is a popular topic, and there are several approaches to address those overheads. For example, modern operating systems offer system calls that combine several operations into a single invocation. However, this is often limited to very specific use cases and operations. Next, there are approaches like IOU ring and flexible system calls that avoid system call overhead entirely by allowing invocation through memory. But those approaches require kernel-side polling, which also costs CPU cycles, and also make system calls asynchronous, which complicates the programming model for the user processes. Finally, there are kernel bypass approaches like DPDK that plug devices directly into user processes. Now, this allows I/O through the device without going to the kernel, but it also shifts the burden of device management to the process and requires implementation of the device driver along with all the higher level abstractions like network protocols in user space. The bottom line is that none of the above is either generic enough or can be introduced into existing software without requiring massive re-architecture. In our work, we propose Privbox, which is a new mechanism for system call intensive workloads that allows system calls with less overhead. Privbox allows user programs to execute their system call intensive code paths inside a new semi-privileged yet sandboxed execution mode. Under Privbox, system call entry and exit are 2.2 times faster than a traditional system call. Additionally, system calls under Privbox retain their familiar and synchronous nature, and adoption of Privbox does not require massive code changes. For example, during our evaluation, we modified memcached key value store to use Privbox, and it took us under 1 hour, and it required less than 70 lines of code. Now, to provide a bit better understanding of what Privbox is about, we are going to compare it to regular execution. And in both cases, we have a sample application that has two functions, a main function and a do.io function that, as its name suggests, does a lot of I/O. In case of regular execution, main function invokes do.io through a function call, and do.io performs many I/O operations through the system call interface. In regular execution, our sample application crosses kernel user space boundary many times, which has considerable overhead. On the right-hand side, we can see execution with Privbox. In this case, main function loaded do.io function into a Privbox environment and invokes do.io code through Privbox Mechanism. Privbox executes do.io code in a privileged CPU mode, for example, ring 0 on x86 architecture, but it also sandboxes it to ensure system safety. Under Privbox, do.io can perform I/O simply through a function call. And this is because Privbox exports a special system call gate function that provides system call functionalities. Invocation through the gate function involves less steps and is therefore much faster than a traditional system call instruction. All in all, under Privbox, sample application crosses the boundary between user space and kernel fewer times and therefore spends fewer cycles on system call overheads. Now, to enable this execution with elevated CPU privileges, we introduced semi-privileged execution mode, a new mode of execution for user processes. This new mode is based on the existing kernel mode Linux work and allows execution of user space processes under ring 0. In our design, process is transferred into semi-privileged execution mode when code is invoked inside Privbox, and it returns to regular execution when code inside Privbox finishes its execution. Now, aside from running with elevated privileges and the ability to access system calls with less overhead, semi-privileged execution and regular execution modes are semantically similar from the operating system perspective. In both modes, processes are subject to all the same permission checks and other security-related mechanisms. And in both modes, processes are preemptible, are subject to scheduler decisions, and are scheduled out when they perform blocking operations. Process in semi-privileged execution mode runs almost exactly the same like a regular process. Now, in addition to the semi-privileged execution mode, Privbox also introduces a system called gate function, which is simply a function inside kernel memory. Its interface and implementation are very similar to the regular system call handler code, but it skips several time-consuming and now unnecessary steps. Through the gate function, Privbox code can branch into system call execution with minimal overhead and without the requirement to change privilege level. Now, I want to talk a bit about the workflow and lifecycle of programs under Privbox. First step in using Privbox is to decide and mark which parts of the program are going to be invoked through Privbox. Once developer identifies and marks relevant code, program has to be built with a custom compiler. At this step, a custom compiler builds marked code with Privbox-specific instrumentation. This added instrumentation is required to ensure safe execution of the code inside semi-privileged execution mode. It is important to note that the added instrumentation introduces overhead to the code and therefore slows it down. So while it is possible to annotate and instrument the whole process rather than just the system call intensive parts, it is highly suboptimal. The third stage happens at the execution time of the program. Program must load all its instrumented code into a Privbox environment. And at this stage, Privbox verify runs and ensures the code is safe by checking that the required instrumentation is present. The last stage is the actual invocation of code inside Privbox. When system call intensive code is needed, it can be invoked inside the Privbox environment. And when invoked, Privbox transfers control to the instrumented code under semi-privileged execution mode. Now, let's talk a bit about the first step of marking and adjusting code to Privbox. Again, we are looking at the same sample application from the previous slides, which has a main function and a do.io function. First, the developer must identify and mark system call intensive code. In our case, this is the do.io function. As you can see on the right, we have added Privbox marker annotation to the code. During program compilation, compiler will inject instrumentation into code that has Privbox annotations. Next, we direct the program to load annotated code. In this example, we load a do.io function into Privbox environment with a Privbox load call. And finally, we replace function call invocations of do.io with invocation through Privbox mechanism. In our case, the Privbox invoke call is responsible for that. All in all, porting to Privbox requires minimal and straightforward code changes. Additionally, this model suits well programs with IO threads. IO thread code can be surgically marked, so instrumentation is limited and does not slow down the rest of the process, while IO thread itself will be enjoying Privbox execution and faster system calls. Next, I want to talk a bit about safety of execution inside Privbox. The most obvious issue with Privbox is that it executes code under kernel-like privileges, while on the other hand, code running inside Privbox is provided by user and can be malicious. So if left unrestricted, user code can gain complete access and control of the system. To address this, we sandbox execution inside Privbox. Our high-level criteria for safe execution under Privbox is that we do not allow any new kinds of access through the use of Privbox. Or in other words, the only things that code under Privbox should be able to perform are the same things that it could perform outside Privbox in regular execution. In more detail, we require the following properties from the code we allow into Privbox. First, no privileged instructions. Privileged instructions are all those instructions that require elevated CPU privilege level. They are not allowed during regular execution of user processes, so we do not allow them inside Privbox code either. Second, we require that loaded code does not perform arbitrary kernel memory accesses, as kernel memory is also not traditionally accessible to user space processes. And finally, to ensure the first two properties hold over time, we require that the code inside Privbox branches only to other verified code. It should not be possible to circumvent our sandbox simply by branching elsewhere to some unverified code. Next few slides, we will talk a bit about the compilation and verification processes. First, I want to mention that our instrumentation and verification methods are inspired by native client work. Now, to take advantage of Privbox, as we have mentioned, annotated code must be compiled with a custom instrumenting compiler. Our custom Privbox compiler is based on the safety properties from the previous slide and generate code that does not violate them. Privbox instrumentation logic happens at the very late stages of the compilation where machine instructions are generated. We look for instructions that could potentially violate the safety properties and transform them into equivalent but verifiably safe sequences. Next, there's the verification process. Verification process happens each time user program loads new code into Privbox. When code is loaded, the verifier disassembles the code into machine instructions and ensures the instructions inside do not violate the safety properties. If a verifier is not able to assert the safety of some instruction sequence, then load operation is rejected, and that code will not be able to run inside Privbox. Now, there's one major challenge in verification through disassembly on architectures with variable length instructions, for example, like x86. The same buffer, when disassembled at different offsets, can result in completely different instruction sequences. Now, like the example on the right, we can have code that when we disassemble it at one offset, it yields a sequence of completely benign instructions. But if we disassemble it at some other offset, it will yield us a privileged instruction, for example, one that writes to a control register. To address this, we introduce the notion of code chunks. A code chunk is a fixed in size and aligned in memory sequence of instructions. In Privbox, we use code chunks of 32 bytes. Under Privbox, we require that all loaded code is packed into code chunks, which basically means that no instruction can cross chunk boundary, and that each chunk aligned address contains a valid instruction of the program. In addition, we verify two properties. First, that each code chunk, when disassembled, is exactly 32 bytes long. So after its last instruction, execution continues from the beginning of the next chunk. And second, that all indirect branches target only chunk-aligned addresses, which means that they target a valid and verified instruction. The two requirements allow us to address the original concern of variable length instructions. As long as we disassemble code chunk by chunk at aligned addresses and ensure that all branch targets are aligned, we can be certain that process will execute only instructions the verifier has checked when it originally disassembled the code. Next, let's talk a bit about instrumentation and verification of machine instructions. First, we deal with privileged instructions. Privileged instructions can be easily identified when code is loaded and disassembled, and in case we find such instruction, we simply reject the code. The next are the load and store instructions that read and write memory. Effective address of those operations is calculated from memory operand of the instruction. Memory operand usually refers to register values, and therefore, effective address usually only known at runtime. Our main concern in load and store instructions is their ability to access kernel memory. And to ensure a load or store instruction is safe, we convert it into the following instruction sequence. First, we calculate the effective address of the original memory operand. Then, we clear the most significant bit of the calculated address. And finally, we replace operand of the original instruction with sanitized address. Correctness of this transformation hinges on the traditional layout of virtual memory. If we recall the layout that appears on the bottom of the slide, we can see that kernel addresses always have the most significant bit set. Therefore, an address with the cleared most significant bit cannot be a kernel address. This operation is also valid for user space addresses, as they always have most significant bit cleared, and therefore are completely unaffected by this transformation. Third type of relevant instructions we take care of are indirect branches and returns. Now, indirect branches and returns move instruction pointer to address stored in registers or memory. And similar to load and stores, targets of indirect branches are only known at runtime. With indirect branches, we have two concerns. First, we want to avoid branches to kernel memory. And second, we want to avoid branches to other unverified code. To address the first part, branches to kernel memory, we implement the same technique as load store instrumentation, and we clear the most significant bit of the target address. The second part of targeting only verified code is handled by clearing the 5 least significant bits of the target address, which ensures the resulting address is a multiple of 32 bytes. Combining both operations, indirect branches and returns can target only non-kernel addresses that are 32 bytes aligned. If we recall, Privbox code is packed into code chunks, and each 32-byte aligned address contains a verified instruction. However, by itself, this instrumentation is not enough, as it still allows branching to any 32-byte aligned address in user space, even outside Privbox, and we handle this shortcoming by the mechanism we present next. The final part of the sandboxing design is the memory layout that we use under semi-privileged execution mode. There are 3 main parts of our memory layout. First, there's the Privbox code region. It resides inside user memory and contains the code that the process has loaded into Privbox. It is readable and executable by user code, but it is writable only by the kernel. And the only way to introduce new code into this region is by loading it into a Privbox environment. Next, there is the user memory. Under Privbox, user memory is similar to user memory under regular execution. Only difference is that it is not executable. This is required to make sure Privbox code cannot branch to this memory region by mistake or through malicious intent. And this, along with the branching instrumentation we have seen in the previous slides, ensures Privbox code cannot escape Sandboxed by branching. Instrumentation we have seen ensures branches target only non-kernel 32-byte aligned addresses, and under this memory layout, the only executable memory in this range is the verified Privbox code. Now, the last part is the kernel memory, which is mapped and accessible to Privbox code. This allows fast invocation of system calls through the system call gate function. And as we have mentioned in previous slides, arbitrary and undesired memory accesses to the kernel memory are restricted through the instrumentation. Now, during our work, we have also noticed that load store instrumentation is responsible for a significant part of the sandboxing overhead. And to address this, we propose a new hardware mechanism named SPAP, or semi-privileged access prevention. SPAP mechanism can be used to detect and prevent kernel accesses performed by code running under semi-privileged execution mode. SPAP works in a very similar fashion to the existing supervisor mode access and execution prevention mechanisms of x86, and we expect it to be of very similar and minimal overhead. On the bottom right, you can see performance of Redis when compiled under different levels of instrumentation. It can be seen that instrumentation required under SPAP is considerably faster than the full instrumentation needed on today's hardware, and is only slightly slower than the uninstrumented version. The reason for this is that under SPAP, our sandbox approach no longer needs to instrument loads and stores, and also can use a lighter form of instrumentation for branching instructions. Finally, I want to present our evaluation results. The results are measured on a prototype we have built based on the presented design. First, we measure the entry overhead of system calls under Privbox. When code is running inside Privbox, system call entry and exit take roughly 415 cycles, which is 2.2 times less overhead than system call instruction on a system that requires page table isolation. Additionally, we evaluated the workload that isolates all system call work into dedicated threads. And in this workload, we have compute threads that process requests from clients, and we have IO threads that communicate with clients over socket interface. Importantly, our compute threads and IO threads communicate among themselves over memory without the use of system calls, so all the system call work is isolated to the IO threads. In the graph below, we can see performance of our benchmark under Privbox relative to the performance when using system calls. In this measurement, we limited the size of send and receive operations performed by the IO threads, and the result of this is that the smaller IO size is, the more system calls are required to read each request or to write each response. IO sizes can be seen on the x-axis of the graph. We can see that for a very small IO size, which is translated to a very high rate of system calls, Privbox variant outperforms the system call variant by up to 72%. Finally, we evaluated some real-world workloads. We present measurements for Redis and memcached, both popular key value stores used in a wide variety of applications. It is worth noting that in both cases, for simplicity, we instrumented the whole program, which is, as we have mentioned earlier in the beginning of the presentation, is heavily suboptimal. Therefore, the result we present can be considered as a lower bound for performance gain, as more accurate porting to Privbox with less unnecessary instrumentation is likely to perform better. Now, despite all this, we were able to improve performance of the workloads by up to 7.6% on today's hardware, and we expect to see an up to 11% improvement on hardware that supports SPAP. Now, to conclude, we present Privbox, which is a new mechanism that allows faster access to system calls for system call heavy workloads. Privbox adoption is simple, straightforward, and does not require software rearchitecture. Under Privbox, system call overhead is 2.2 times lower than that of a regular system call instruction. We also present results of up to 72% improvements in workloads designed to take a direct advantage of Privbox, and we present a lower bound of 7% speedup for workloads like Redis and memcached. And finally, oral code is available and documented along with all of the experiments we have presented on GitHub. Thank you.